So I'm going to talk about an existence and uniqueness theorem. And basically every time there's a new type of differential equation, there's going to be an existence and uniqueness theorem. And these kind of seem like very notation heavy, very wordy theorems that don't seem to have any bearing. Basically what they do is they guarantee what we like about math. What do you like about math? Maybe you didn't know this, but what you like about math is that there's one right answer to everything. Back in third grade, if you like math, they say, okay, well, what's 3 plus 4? And you say 7. And it was good that the answer was 7. The answer didn't change from time to time like some other classes that were not as fun. Okay, maybe they were fun for you. But that's what people like about math. That's what these very wordy, very notation-heavy theorems guarantee in the study of differential equations. So let's look at it. I'll try to explain it piece by piece, and hopefully it'll be somewhat meaningful to you, even if you're an engineering major and you may not care about the theoretical side. All right, so here we go. Here's the existence and uniqueness theorem for first-order linear differential equations. I wrote it down so that we could just talk about it. Okay, so we have this first-order linear differential equation. This is the form we had it in before, right? If it's not in this form, you divide both sides by whatever's in front of y prime, get it in this form. So we have these functions q of t and g of t. And what this theorem says, if q of t and g of t are continuous on some open interval, in calculus, intervals are going to be open usually. Sometimes they're continuous on closed intervals, actually, but we're only going to require that they're continuous on an open interval and that our initial value, this later is going to be our initial value, is in that open interval. And what that means is we guarantee that it's nice enough that when we integrate, because remember our I of t was e to the integral, some integral of q of t dt. So if it's not continuous, I might still be able to integrate, but I'm going to do things that are too funny, basically to the function, and my solution might not satisfy the original function. So this is guaranteeing that the functions are nice enough. Then it says, then for any choice, I can pick any initial value I want, as long as the independent variable is in the interval. Then I have a unique solution, meaning I only have one solution that's going to satisfy both the differential equation and the initial value. So satisfying the initial value problem. So that's cool. That means as long as functions are nice and my initial value is in here, then I'm good. I have one solution to my problem. Let's look at where this might apply. So this was the last example that we did of first order linear differential equations. And remember I said we would come back to this t greater than 0. Because if we look here, my q of t is 2 over t, and my g of t is 4t. 4t is continuous everywhere, so I'm good. 2 over t is not. 2 over t is not continuous at t equals 0. So I need an interval, and the interval can be infinite. So here my interval goes from 0 to infinity, not including either one. I can't include infinity, but I do not include 0. That means my q of t is continuous in this interval. That's good. That's what the t is greater than 0 is saying here. Making sure that I have a unique solution. If not, then I may not have a unique solution. As a further illustration of why an existence and uniqueness theorem is important, I'm going to show you a differential equation that does not have a unique solution. And that's this one. dy by dt is y to the 1/3. Now notice this is not a linear differential equation because y to the 1/3 is not a linear function. So the conditions of the theorem do not apply. But this is just an example to show something that's not unique. What's nice is that it is separable, so we do know how to solve it. Great. We're going to keep the dy on top. We'll multiply both sides by dt, divide both sides by y to the 1/3. So dy over y to the 1/3 is dt. I'm going to say, by the way, that y was not 0 because I divided both sides by y to the 1/3. I will integrate both sides. Then I get, this is y to the negative 1/3, so add 1 to the exponent is y to the 2/3, and then divide by the exponent, I get a 3/2 equals t plus some constant. Right, and then let's solve. Okay, so y to the 2/3 equals 2/3 t plus, I'm just going to call this some other constant, c1, so that I don't have to write 2/3 c. And then I will raise this to the third power. So y squared, raise both sides to the third power. It's 2/3 t plus c1 cubed. And then I have a square, right? So I get two solutions. So y is actually going to be either positive or negative the root of this thing, 2/3 t plus c1 cubed. Okay. Now, let's say we have some initial value. Let's say y of 0 is 0. Okay, so I'm hoping for a unique solution because that's why I like math. I'm going to sub 0, comma 0. I get 0 equals plus or minus the root of c1 cubed. Okay, so c1 is 0 regardless of the plus or minus, right? So, but then I sub this back in. So I get y equals plus or minus the root of 2/3 t plus 0 cubed. And I haven't figured out if it's plus or minus. There was a problem a few lectures ago, I think from last week, where the c value also took care of whether it was plus or minus, because I could replug this initial value in and then figure out if it was plus or minus. Here I can't do that. If I plug this in, this actually still works. We get 0 equals 0 regardless of whether we take the plus or minus sign. So this root basically ruined everything, where it didn't in the previous problem that we saw with this. So this initial value problem, I'll write this up here, y of 0 equals 0, does not have a unique solution. So there can be cases where maybe in this type of differential equation we don't have a theorem, or this thing wasn't nice enough. Maybe it didn't meet an extra condition that was here.